Okay, welcome back, everybody. Well, it looks like we got a small group today. No, wait, one more. Okay, well, as I mentioned last week, and I haven't sent the email yet. I'm still preparing it. I want to do is add some more fine tune a little bit. But basically, the Tuesdays from today forward, we will use them to do the chapters. We don't have that many chapters. And then the Thursdays, we'll use that day to either talk about the problems, but if no one has any questions, what I'll do is I'll go over the worksheets. So also to give you an opportunity to, come in with questions. We can go over any of the problems for whatever chapters you may have a question about. Because we will, when you do the comprehensive, the final will be comprehensive, so cover all the chapters, okay? So what I'll do today, the plan is I'll finish up chapter 12. We are on slide, pardon me one moment. We're on slide 9, we'll knock that out. And if you have any questions, I will continue answering the questions, but I won't jump into 13 until next Tuesday. And if there are questions, then, I'll stay here, remain till my time's up at the allotted time. But other than that, you're welcome to, log out. It's up to you. Okay. All right. Where were we? We were on slide number 9. And we had just finished talking about using Avogadro's number to calculate the number of atoms. Now, Avogadro's number, like any factor, is a ratio. Avogadro's number is 6.02 times 10 to the 23rd atoms, molecules, units, whatever. It's a counting unit, like dozen, per mole, okay? 1 mole is equal to 6.02 times 10 to the 23rd units. And we can flip that ratio either with the number on top or Avogadro's number in the denominator. And how we set it up depends on the question and what units we need to get rid of. So we did this example. We had how many calcium atoms are in 0.250 moles of calcium. Okay, we're using Avogadro's number with the 6.02 times 10 to the 23rd atoms in the numerator because we want to calculate. Hold on one second. All right, so you can see here how the units cancel out. This goes back to where and I overemphasize this, and I will continue to emphasize this. This goes back to how we did the first couple of chapters. Remember when we were doing conversion factors, I talked about follow the units, make sure you got it set up properly, because we're going to use that technique when we do calculations, chemical reactions, and we're getting close to that stage. Okay, so keeping track of my units, you can see moles canceled, leaving me with the units of atoms, which is what the question asked for. Okay, and then the rest is on you, plugging in that number into the calculator. Refresh your memory on how to use the scientific notation function of your calculator. Second one here, notice here we're looking for how many molecules, how many moles is if we have an X number of molecules. It's specifically 3.75 times 10 to the 27. Again, we're using Avogadro's number, and we are dividing by Avogadro's number because we are looking for moles, which is set up in the numerator, okay? Molecules cancel out. It is molecules because that is what the question asked. It could have been atoms, it could have been whatever units the question asked for. Again, I overemphasize, I continue to emphasize that Avogadro's number units is dependent on what you're searching for. It is just a number like the number dozen. You know, when you say dozen is, it's 12 units per dozen, okay? It's like 12 units per dozen. Avogadro's number is just a different, bigger number, 6.02 times 10 to the 23rd units per mole, okay? And we can write it in either manner, with moles in numerator or moles in the denominator. Okay, so we ended up here. And this is calculations, notice, you know, up to this point, we've been just dealing with, you know, moles or atoms. But now, you know, keep in mind, when we're in the lab actually doing experiments and we're going to do calculations, we don't have balances that measure in moles. We have balances that measure in grams. And so even though we use moles in our calculations, we need to convert that unit moles into something that's weighable, and that's grams. So we have to learn how to go from grams to moles and moles to grams, okay? Because the molar mass of any compound has the units of grams per mole, okay? Just like the atomic weight has the units of grams per mole. And the molar mass, the only difference between molar mass and the atomic weight is the molar mass is the sum of the atomic weights of all the atoms involved in the structure of the compound that you're working with. So obviously they're going to have the same units. Molar mass with the units of grams per mole is another ratio, okay? And so we can write that as either grams over moles, whatever grams is, X, you know, normally moles is 1, X number of grams per mole, or we can write it as 1 mole over divided by X grams, okay? So let's do some examples here. Here, the question is, how many grams is a 1.667 moles of oxygen gas, okay? And so we write down, as any of the problems that we've been doing up to this point, is we write down what we are looking for, okay? We are looking for grams of oxygen gas, it's O2, and we are given 0.1667 moles of oxygen. Okay, so that means that we're going to have a conversion factor because we're going to get from moles to grams. So we're going to have a conversion factor that obviously has moles in the denominator and grams in the numerator. Okay, and that fits the characteristics of molar mass, grams over moles. Our moles cancel out, right? And so basically, we're going to need the molar mass of oxygen. Bear in mind that it's oxygen gas, is diatomic, okay? So therefore, we need the molar mass of oxygen, which would be 2 oxygens, which is 32 grams per 1 mole, okay? So with that, you just plug it into the calculator, and you should have a number of 53.34 grams of oxygen. And so if you have 1.667 moles of oxygen, it has a mass of 53.34 grams. Okay. Again, molar masses, the atomic weights, the molar masses are not utilized in determining number of sig figs. So when we look at 1.667 moles, that is a measurement, okay, because you went from grams at one point. Well, it is a measurement, I should say, and therefore it will have 4 sig figs, so our answer should have 4 sig figs. All right, now here, they're asking how many moles is 45 grams of silver, okay? How many moles And so we started off with 45 grams of silver. And we need to figure out how many moles that consists of. Okay, so that means I need a atomic weight. Okay, because I want grams to cancel and I want moles not to cancel. Grams cancel. Okay, so that tells me we need the atomic weight of silver, which is what, 107, double checking, 107.87. So it's 107.87 grams per 1 mole. Okay. Check my units, grams cancel, leaving me with units of moles of silver. So it's been properly set up. Now it's a matter of you plugging those numbers into the calculator. So that corresponds, 45 grams of silver corresponds to 0.42 moles of silver. Okay. Now, this exercise here, notice, as I mentioned, is we're going from, right now we're going from grams to moles. Okay. And so if we were doing a calculation of, let's say, silver going on to make some, I don't know, some silver chloride compound, for example. Well, if I had 45 grams of silver, I need to calculate how much silver chloride. There's some other processes here, but I'm just going to show you. I want to show you an example. Okay. Here I am with 45 grams of silver. I need to get the silver chloride. Well, I can't go directly. Okay. I need to go through moles. Well, before I do anything, I need to convert my 45 grams of silver to moles of silver. That's what I did right there. Now, at that point, I can now go to whatever else I need to go to. Okay, so that's our common factor, is being able to learn how to get from grams to moles and moles to grams. Okay, going back and forth. All right, because we can't get from point A to point B without going through that common factor, in this case, moles. Also notice that with respect to what we did with the first example, we went from moles to grams, okay, unit-wise, moles to grams, and guess what we did? We multiplied by the molar mass, okay? And the second example, we went from grams to moles. And what do we do there? We divided by the molar mass. So up here, we multiply by mm, molar mass or atomic weight. Down here, second example, we divided by the molar mass or / atomic weight, depending on what you're doing, okay? If it's an atom or a molecule compound of some sort. Okay. But if you don't see that right now, continue with the units, keep following with the units, and eventually as we do more practice and you do more practice examples, you'll see it, and then you can create some not shortcuts, but shortcuts for you. Okay. All right. Here they want to know how many grams is 0.0554 moles of water. Okay. So we start off what we're given. Moles of water. Okay. And we're looking for a number of grams of water. That means we need a conversion factor again. That takes us from moles, we want moles in the denominator and grams in the numerator because we want our moles to cancel. So we need the molar mass of water. So water, the formula for water is H2O, okay? And so we got oxygen, which is 16.00. We got 2 hydrogens, each one at 1.01, which means it's a total of 2.02. And so we have 18.02 grams per mole for the molar mass of water. So we got 18.02 for 1 mole. And we multiply that by 0.054 moles. And that gives us the answer of 0.998 grams of water. So starting off with 0.054 moles of water, that corresponds to 0.98 grams of water. Okay. Again, we have moles, we go to grams, we multiply by the molar mass. Okay. Pardon me for 1 second. I need something came up. I got to stop here real quick. I'll be back in about 2 minutes. Okay, I'm back. Sorry about that. You got a couple of cats here trying to tear up the place. Okay, so the last one here is saying how many grams is 4.75 times 10 to the 16 atoms of potassium. And so what we're looking for here, again, write down what we're given. We got 4.75 times 10 to the 16 atoms of potassium. And we are needing to go to grams of potassium, okay? All right, so we have atoms of potassium, so that should tell you, okay, we got Avogadro's number here. Okay, we need to use Avogadro's number. All right, so I'm going to put atoms in the denominator, okay, because I want to cancel atoms out and I want to get to moles. Okay, moles is a common factor, whether we're going from grams or we're dealing with atoms or molecules. We got to get to moles so we can proceed from there to whichever direction we need to go to. All right, so that means that we got to put Avogadro's number in the denominator, 6.02 times 10 to the 23rd per 1 mole. Okay, our atoms cancel out, leaving us with moles of potassium. Okay, well, we're trying to get to grams, so we need moles to be canceled out, moles of potassium, and give us grams of potassium. So grams over moles is basically the atomic weight, right? Okay, so potassium is what, 39.10. So it's 39.10 per 1 mole, 39.10 grams per 1 mole of potassium. Moles cancel out, atoms cancel out, leaving us unit-wise with grams of potassium, which is what we are being asked to calculate. Notice we put 2 conversion factors side by side. When we start doing calculations, you're going to see here that we're going to use an average of about 3, at the minimum 3 conversion factors to get us from bananas to oranges, if you will. All right, so we got it set up. The units look like they cancel out okay. Now it's a matter of you plugging in the numbers and running it through your calculator, and you should come up with 3.09 times 10 to the 6 grams, okay? All right, 6 grams. Now, the question here is, notice this is kind of ambiguous, but I want you to think about this for a second. Normally, the calculations that we've been doing so far have been measurements. Moles is a measurement coming from grams, so going from grams to moles, back and forth. It is a measurement, and so using our molar mass and so forth, they're not. Molar masses are not utilized in determining how many sig figs, right? Now we get this one here, and here's the thing. The number 4.75 times 10 to the 16, that's a whole number, okay? And earlier I said, well, Avogadro's number is just a number like a dozen. It's an exact number. And so, and then the atomic weights, it's the average of the isotopes who have an infinite number of sig figs. So technically, none of these factors would determine how many sig figs you would have, because we got a whole number here to begin with, 4.75. And then Avogadro's number, again, is the exact number. And then the atomic weights are ambiguous with respect to sig figs. And so if you were to put any more numbers there, 3.09, that would be okay. However, Canvas is not that smart to figure that out. So as a guideline, when realizing that you're dealing with whole numbers, knowing that Avogadro's numbers is not going to be used as to determine how many sig figs, nor is the atomic weight, then just kind of use the number you're given in the problem. So it has 3 digits, so your answer should have 3 digits. If you were to write more than that, you should. I wouldn't count I wouldn't count, because you have an infinite number of sig figs here. Does that make sense? Only for these type of examples, only for the last example that we just did. Normally, you're dealing with measurements, okay? Here, you're not. You're dealing with exact numbers, right? Does that make sense with respect to the last one? And all the other ones, they're dealing with measurements. These are measurements. It took a tool to measure a weight or something, and that in itself has a degree of uncertainty. Exact numbers don't have a degree of uncertainty. 1 is 1, 2 is 2, exactly, right? All right. So a side note there. All right, so this is dealing with the molar mass or the atomic weight, which has units of grams per mole, and that's going from moles to grams and vice versa. And we also use Avogadro's number to get us from number of molecules, number of atoms to an actual mole, or to go all the way through to calculate the an actual mass, okay? Now, in the beginning, when we were talking about the physical states of gases, we said that gases do not have a volume, don't have a set volume. They have the volume, whatever container that they have. Well, that wasn't, quote, 100% correct, okay? So, but we need to clarify that, okay? Not 100% correct, unless you are at what is called STP, which stands for Standard Temperature and Pressure, okay? STP, which is right here, okay? STP is 0 degrees Celsius and 1 atmosphere. Standard temperature is 0 degrees Celsius and 1 atmosphere pressure. We are right now approximately 1 atmosphere pressure. If you're on top, let's say in Colorado, your atmospheric pressure would be a little bit different. And as you go the next number of feet down in the water, the pressure obviously increases. So anyway, under those conditions, 0 degrees Celsius or 1 atmosphere, the following is true about gases, okay? When you take any gas, for example, hydrogen, fluorine, ammonia, xenon, methane, if you have 1 mole of that particular gas, as in the case we just talked about, if you have a dozen, you have 12, but if you have a mole of anything, you're going to have Avogadro's number, 6.02 times 10 to the 23rd molecules of that particular gas, okay? Now, obviously, their molar mass is going to be different because they're different size atoms. Hydrogen's molar mass is 2.02 times 2.02 grams per mole. Xenon, 131.29 grams per mole. So obviously, even though everybody here there's 1 mole and everybody has the same number of molecules, they're all going to weigh different. It's no different than, using the analogy of eggs. I got a dozen small eggs, a dozen medium eggs, a dozen large eggs. They're all going to weigh differently, right? Because you got small, medium, large, there's different sizes. But what they all have in common is there's a dozen. And that says, I got 12 of everything. Well, the same as here, okay? Now, what happens under these conditions at 0 degrees Celsius and 1 atmosphere, there is a relationship between the volume of the gas and the moles of gas. And that relationship is what we call a molar volume at STP, which consists of 22.4 liters per mole, okay? Think about this for a second. At 0 degrees Celsius and at 1 atmosphere, if I have 1 mole of any gas, hydrogen, oxygen, methane, xenon, whatever, it would occupy an exact volume, well, not exact, because there's a measurement, so there's some air involved. It would have a volume of 22.4 liters per mole, okay? 1 mole of gas will have a volume of 22.4 liters at STP, okay? Also remember something else, that 22.4 is a measurement, and therefore it could be a factor if utilizing your calculations to determine how many sig figs your answer should have, okay? I repeat that. 22.4 liters is a measurement. It's not an exact number, and therefore it could be a factor in the final sig fig determination for your answer, okay? All right, so that means that 22.4 liters per mole, guess what? It's another ratio, liters per mole, or moles per liter, okay? And I can use this for calculations of gases, STP, because if I know the volume of a gas at STP, guess what? I know the moles. And if I know the moles, guess what? I can calculate either the grams of that gas or actually calculate using Avogadro's number how many molecules of gas I had, okay? All right, well, let's run through some examples. All right, so this is just to state what I just stated. At STP, 0 degrees Celsius and 1 atmosphere, 1 mole of any gas will occupy a volume of 22.4 liters, okay? And as I stated earlier, I can write that 1 or 2 ways, with liters in the numerator or liters in the denominator. Which one I need depends on the question. For example, what is the volume of 1.25 moles of argon gas at STP? These type of equations are important that it be told and it said or stated in the problem that you are at STP, or they may state 0 degrees Celsius and 1 atmosphere, which is STP conditions. And so only in those conditions can we do this calculation. If it doesn't state STP, nor does it state any other temperature or atmosphere, any other one than 0 degrees or 1 atmosphere, you cannot do the calculation. It won't work, okay? All right, so as we do anything else, we write down what we're given, 1.25 moles of argon, okay? And we're looking for the volume. So we're looking for the volume of that gas, volume of argon, okay? So we're at STP, we have moles, so guess what? I got moles in the denominator and I got liters in the numerator. Okay, so 22.4 liters per 1 mole check my units, moles canceled, leaving me with units of liters, which is what the question asked for. Okay. All right, so that means that that is equal 1.25 moles of argon gas at STP would occupy a volume of 28.0 liters. And then ask yourself, like any of these calculations you do, does the number make sense relative to the mathematical function that you're doing? Okay, and this is what I mean. Well, look at this. You are 1.25, almost a quarter, and 1.25 moles of gas. Well, we know that 1 mole gas will occupy 22.4, and 0.25, which is a quarter, would mean I got to add a little bit more to it, right? So my answer should be greater than 22.4, a little bit greater, and that number of 28.0 is consistent with the mathematics that we did here. Okay. And that's what I'm talking about when I say, you know, does the answer make sense? Check your answer based on the mathematical function that you did to it. Does that make sense? If you were to divide by accident and instead of multiply, let me see for a second, you would get, let me see, 1.25 divided by 22.4. Let's say you had an answer of 0.005 as an answer, because you inadvertently divided by 22, and you will get 0.055, thinking it's liters, but you inadvertently divided by 22.4, and you have this answer here. That should be a flag to tell you, whoa, it doesn't make sense, given what I'm given, that I have over 1 mole of gas, and I know that 1 mole of gas would occupy at least 22.4. So that wouldn't be correct, that answer there. So something must have occurred, an error must have occurred, and it gives you an opportunity to check your answer and make sure you did the correct mathematics. Okay. All right. Next one, number 2. How many moles is 30.4 liters of oxygen gas? All right. So we got 30.4 liters of O2. And we need to know how many moles that consist of. Okay. Well, liters cancel in the denominator, moles in the numerator. 22.4 in the denominator. Okay, liters cancel, leaving me with moles. And so if you have 30.4, again, look at your answer. It's slightly, it should be slightly above 1 something, right? Because at 22.4 is at 1, and you're only about less than 8 more units to get at 30. So your answer should be, clear it, 1.36, which is consistent with the mathematics that you did. Notice my sig figs, I start off at 30.4, 3 sig figs, 22.4 could be a factor in the sig figs, okay, because it's a measurement, but in both cases, they're both 3, so my answer should have 3 sig figs. All right, so in the examples 1 and 2, we start off with moles, went to liters, then we went from liters back to moles, okay? Here, the next one, they're asking you to go from liters to mass, okay, to get a weight. All right, so what is the mass of 4.5 liters of chlorine gas at S2P? And so we have 4.50 liters of chlorine gas, okay, and we need to know what is the mass, so that's how many grams of chlorine. All right. And so we are going to need a couple factors here, right? I'm going to need the first factor to get me from liters to moles, which would be the relationship of 22.4 liters per mole at STP. And then once I got moles, then I just simply need the molar mass of chlorine gas to get me to the mass. Okay, and so you should have something that looks like this. Okay. Liters cancel out. First unit gets me into moles, okay, of chlorine gas. And then from moles, I need to get to mass. So I need the molar mass of chlorine. And they say chlorine gas, that's an indication that you're dealing with Cl2. They didn't say chlorine atom, okay, because chlorine gas tells you, okay, that's diatomic. Anytime oxygen gas, hydrogen gas, anytime they describe those 7 diatomic molecules, you know, it's either a gas or, you know, have to be aware of the ones that are gas that they're diatomic, okay? Therefore, the molar mass will be 35.45 times 2 or 70.9 grams per mole for the molar mass of chlorine gas because it's diatomic. All right, so 4.5 liters would have a weight of 14.2 grams at STP. Again, none of these calculations would work if you are not at STP. So this flow chart, which is going to be one of the second flow chart that we're going to use in the calculations, will help you get around these problems, okay? These works that we're going to be doing, because notice here, I can get from grams, let me restate, let me do the color here, from grams to atoms, okay, I can get from there, but only through moles, okay? I can't go directly. And I can get from grams to volume, but also only through moles. And any combination thereof, because here, this flow chart really is a double side. It's a double arrow. I can go in both directions here. Okay, let me clear this up a little bit. And so I can go from there to there, in both directions. Okay. But I can't do anything unless I go to moles. Moles is the common factor for all these calculations, okay? Common factor. And the yellow part is only true if you are at STP. Okay, if you're not at 0 degrees Celsius and at 1 atmosphere, the yellow, you cannot do the yellow part, cannot get to a volume or go from a volume, okay? Now we can go from volume to this direction to atoms, or I can go from volume all the way to grams. But only through moles, okay? Only through moles. Any questions right now before I continue? Any questions? All right, well, here's an example of a problem that's saying how many grams does 17.35 liters of neon gas mass at STP? Or how much, if I have So if I'm at STP and I have 17.35 liters of neon gas, how much does it weigh? Okay. And then if I have the same amount of gas, how many atoms does that correspond to? Are the questions. So anyway, first part, we write down what we're given, 17.35 liters, okay? And we need to get to grams. So obviously, I come out, I got the answer there, 15.6, but we're trying to get to grams. And so my first factor is, because we are at STP, will get me out of liters and into moles, okay? That's my first factor. My second factor is my mass, atomic weight, I should say. To get to mass, I need the atomic weight. And I write it with grams in the numerator because that's what the question asks for. I need to figure out the weight of neon gas. If I have 17.35 liters of neon gas. Check my units, they cancel out. I got grams left over. Everything is where it should be. Okay. So you plug in a number, so you end up with 15.6 grams. Now, here's the thing. I have 3 sig figs right here, 15.16. But I started off with 4 sig figs, so why do I have that as an answer with 3 sig figs? Three sig figs here. This has 4 sig figs. Is my answer correct with respect to the significant figures? Yeah. Remember, that's a measurement, 22.4. So it could be a factor with respect to your sig figs. And in this case, it is. Okay, so 3 sig figs, that's why your answer has 3 sig figs. Remember, the atomic weights are not with respect to sig figs. Okay. And 22.4 has 3 sig figs, and that's why your answer has 3 sig figs. Okay. The second part, how many atoms does that particular volume consist of? So we have the same setup. So start off with 17.35 liters, okay? Eventually your answer should have 4.66 times 10 to the 23rd atoms. All right, so the first one, same conversion factor, because we are at STP, and that kicks us out from volume into moles, okay? Volume of liters into moles of material. Once we're there, all we simply need is the Avogadro's number, and it tells us how many atoms of neon gas. Okay, and so the last flow chart, we were at volume. We went from here to here. Okay. And then we went from that same information, the volume, to that, to atoms, okay? But we went through that through moles. You have to go through moles. Okay. That's the takeaway from this part up to this point. Is if wherever I start out grams, and I need to go learn how to calculate, starting with grams, how to get to moles, and from moles, how to get back to grams. And if you're STP, you are at STP, we're dealing with the gas, that relationship of 22.4 liters per mole holds true. And you can utilize that factor to get you from liters into moles and vice versa. But once you're in moles, you can go take it further one more step and get into grams if you need to, okay? All right, which brings us to density. Well, we did talk about density way back when, but density is, again, a ratio, specifically a mass over volume. All matter has density, okay? And density varies. And it's simply a mathematical calculation of whatever mass you have, and you divide it by the volume that chunk of matter has. That determines its density, okay? Now, we can calculate or determine the density of a gas without even having to measure it. All we got to do is make sure we are at STP, 0 degrees atmosphere, 0 degrees Celsius, and at 1 atmosphere, okay? Because if we take the molar mass and we divide it by the molar volume, we have the units of mass over volume, okay? And so, for example, calculate the density of ammonia gas, which is NH3, the formula is, and we calculate the molar mass, which is 1 nitrogen, 3 hydrogens, that has a molar mass of 17.04 grams per mole. And we are at STP, that means that the molar volume is strictly 22.4 liters per mole. And that means that at STP, ammonia has a density of 0.761 grams per liter. And that occurred because, you think about this, grams per mole divided by liters per mole. Okay, we're dealing with fractions here. If you think about it, it's like taking 1/2 divided by 1/4, right? Well, how do we do that? Well, the denominator fraction, we take it, we invert it, so it becomes 1/2 times 4/1, which is 2. But if you look at the units here, we got grams over moles, unit-wise, invert the units in the denominator, which gives us 2 moles per liter. Moles cancel out, and we end up with grams per liter, unit-wise, which is, by definition, the density, okay? So, you don't have to, if you're asked to calculate the density of a gas at STP, pretty straightforward. Take molar mass divided by the molar volume, and you got it. All right, the last aspect here, almost the last aspect, we'll talk about what is called the percent composition, okay? Now, we figure out how to calculate or determine the molar mass of any compound. Well, first of all, you need the formula, right? And from the formula, if you add up all of the atomic weights from all the atoms, add them up, that gives you tally it up, you get the atomic weight. So if we look at water we know has a molar mass of 18.02. We did that calculation earlier. Water has 2 hydrogens and 1 oxygen. So the total amount of hydrogen contribution to the molecule of water is 2.02 grams per mole of hydrogen, okay? Because there's 2 hydrogens. If we take that and divide it by the total atomic molar mass and multiply that by 100, what that does is gives us the percent composition of hydrogen, okay? So water is composed of 11.2% hydrogen. If we do the same with oxygen, which has an atomic weight of 16, divided by 18.02 times 100, that ends up to be 88.79% oxygen. So water, the composition of water is 11.2% hydrogen and 88.8% oxygen. Okay, and that is true for water wherever you find it, be it here in Arizona or on some planet out there that has that formula H2O, that's the percent composition. Note that the percentages should add up to be 100%. If it doesn't, then check your math. Something probably went amok. All right. Now, with that, we can calculate or determine the percent composition of any compound that's thrown at you. You may not know what it is, and that's okay. As long as you got the formula, you can determine the percent composition. And this example here is asking you to find the percent composition for TNT. Does anybody know what TNT is? Any ideas what TNT is? It's dynamite, okay? TNT, its name is trinitrotoluene, hence the term, the initials TNT, trinitrotoluene. And there is the formula for trinitrotoluene. This particular chemical was discovered by Nobel, aka the Nobel Prize, named after him. He was a chemist that discovered this very explosive material and just made millions with it. Anyway, he took that millions and created the Nobel Foundation. Hence, we get the Nobel Prize out to medicine, chemistry, physics, literature, a bunch of things out there. Anyway, let's figure out the percent composition. And one note about it, when you do these calculations, do use our periodic table with our atomic weights. Yes, we understand you can get a variety of atomic weights all over the place, but bear in mind, you're dealing with Canvas, which is not the smartest software out there. And we've been trying to teach it a variety of answers, and so it's a learning process. But the point is this: by using the periodic table, atomic weights from our periodic table, you lessen the chances of writing the wrong answer. Now, if you're off by 1/10 of a value and you're counting wrong by Canvas, let me know. I would definitely give you credit for it. For example, you might type in, 10.01, and the answer is 10.02. Or Canvas, when it looks for the answer, it's very exact. And there's no degree here. If you're 0.2 or 0.3, it has to be exactly what Canvas understands. So if you ever have a problem with any of the questions and you know the answer is right, let me know, because even a space, if you add a space, Canvas counts it wrong. Okay. Anyway, do use the periodic table from Chem 130. All right, so there's 7 carbons. Its atomic weight, each one is 12.01. So the total for the carbons is 84.07 grams per mole. Hydrogen, there's 5 hydrogens. Each one brings in 1.01. That's a total of 5.05 grams per mole. Okay. The nitrogens, there's 3 of them. Each one brings in, it has 14.01, the atomic weight for each nitrogen. That's a total of 42.02 grams per mole. And then the oxygen, there's 6 of them, each one at 16 grams per mole. That's a total of 96.00 grams per mole. The total molar mass for TNT is 227.15 grams per mole. To determine the percent composition, you simply take the individual atomic weights for whatever atom, in this case carbon, and divide it by the total amount. So 84.07 divided by 227.5 times 100 gives you 37.01% carbon. Hydrogen, it ends up to be 22.2% hydrogen. Nitrogen is at 18.5% nitrogen. And then finally, oxygen brings in a total of 42.26%. Okay? tally that up, that should add up to be 100%, or at least 99.99%. And so TNT has a composition of 37.01% carbon, 2.22% hydrogen, 18.5 for nitrogen, 42.36 for oxygen. And in the real world of chemistry, we do that as a chemist who would make new compounds, synthesize new compounds. We will clean them up, purify the material as best we could, okay? And do a variety of things to it, get it nice and clean, and then ship off a sample for analysis. We knew based on that, just on a bunch of information, numerous other bits of information, what type of structure we are dealing with. And so we could calculate the percent composition, send a sample off for analysis, and then when it comes back, if it was correct, then we'd be very close to what we calculated. And that information, this information, coupled with the other information, would verify that yes, in fact, we have a particular structure in a particular compound. So, all right, so tell you what, try these at home. In fact, if you don't come up with these answers, Thursday is a good time. You can bring it in and we can go over it. So first one is, how many liters is 3.425 grams of carbon dioxide occupied at STP? So if you have 3.425 grams of carbon dioxide and you are at STP, what volume would it occupy? Okay. Still with carbon dioxide, if you have 3.425 grams of the same carbon dioxide, okay, well, okay, if you have 3.4, same amount of carbon dioxide, how many molecules would that correspond to? You should come up with 4.68 times 10 to the 22nd molecules of carbon dioxide. Okay. And if you have 3.0 times 10 to the 15 molecules of carbon dioxide, what would they weigh? What is their mass? And you should come up with 2.2 times 10 to the -7 grams, a very small amount. Grasp that number for a bit. You have a large amount of carbon dioxide molecules, 10 to the 15th, and the total weight only comes up to 10 to the -7 grams. Gives you again a better perspective as to how small these molecules are. So try these at home. If you can't get them, we'll bring them in on Thursday and then we can go over them, okay? All right, well, congratulations. You have finished chapter 12. And I will stop it here.